From KUNC and the NPR network, this is In The NoCo. I'm Erin O'Toole. An innovative cancer therapy inspired by the gripping power of geckos. Scientists at the University of Colorado Boulder studied the microscopic structures on gecko toes that allow the little reptiles to climb walls and cling to slippery surfaces like windows. And that inspired the development of a new material that could help chemotherapy drugs cling onto tumors, enabling less frequent and more effective treatment, potentially with less discomfort and fewer side effects for patients. Wyatt Shields is assistant professor of chemical and biological engineering at CU Boulder. He's part of the research team. So far, they've focused on bladder cancer, which has been in the headlines after CU football coach Deion Sanders announced he'd been treated for it. Bladder cancer affects about 85,000 people in the U.S. each year.
Bladder cancer is a really interesting disease from a treatment and fundamental science perspective. For drugs that are used to treat bladder cancer, they're often administered directly into the bladder by means of a catheter. And one of the challenges that's very unique to bladder cancer treatment is that because we have to go to the bathroom, people on average go into the bathroom 5 or 6 times a day, you have a short residence time of drug within the bladder. And so that leads to a lower efficacy of drug.
And when you say residence time, I'm picturing just the time that a drug is in contact with a tumor. Is that right?
That's right. Yeah. So the idea is that in order for a drug to be active, it has to be located in that proximity so that it can work against those bladder cancer cells. And so the idea is that we want to really improve the time that the drug is in that vicinity.
So you and your team decided to look at lizard toes to play a potential role in this cancer treatment. What were the characteristics that you were looking for?
It's a great question, and it's not really the most obvious place to start when you're thinking about bladder cancer treatment.
No.
We wanted a technology that was adhesive, but not through chemical means. We didn't want any sort of glues or chemical adhesives that would stick around inside of the bladder. Instead, we wanted to create a system that could adhere to the bladder wall, but could do so in a way that was based on maybe a different mechanism. And we discovered that geckos actually have a really amazing way of adhering to surfaces, and that is through nanostructures on their toes.
What is it about the structure of gecko feet that enables them to stick to all sorts of surfaces?
So if you look at a gecko's foot under a microscope, you'll see that they have these little microscopic structures called setae, and they're basically these nanoscale hairs or fibers on their toes. And the idea is that they have a huge amount of surface area because of all of these bristles and fibers and so on. And so when a gecko basically presses into a surface with their foot, it spreads out all of those bristles, and the gecko is able to make contact with a surface through all of these little hairs. So there's no chemical adhesive whatsoever. It's purely just based on the fact that they have these really high surface area structures on their feet. And so we wanted to really create a material that had that same quality so that we could stick this onto a bladder tumor.
Man, this would have blown my mind as a 6-year-old. I thought it was like tape on a gecko's feet.
It is amazing because they can climb on glass, they can climb on wood, on painted surfaces. I mean, really, what's amazing about it is because it's not a chemical adhesive, they're able to walk on all different kinds of surfaces. And if you think about the bladder is a very hydrated environment, right? You have urine, it's liquidy, and so it's hard to stick to that kind of surface in particular, which I think lends itself well to this kind of adhesion mechanism.
So with this knowledge, you and the team developed this sticky material that will cling to a tumor and be able to deliver kind of like a long-acting treatment, basically. How would the treatment for bladder cancer be different with this new material?
The idea is that we can administer this material into the bladder directly over the cancer site. And it's able to stick to that site for several days, maybe even a couple weeks. And over that period of time, it can release this drug slowly. And you can continue to go about your life. You can go to the bathroom. You can do whatever you need to do. And the drug is going to slowly be eluted from that from this material. And the advantage is that you don't have to go back into the clinic and receive multiple rounds of treatment. You can really, hopefully, receive just one or maybe a small handful of treatments. And eventually, the idea is that after about a month or so, this entire system would be completely gone.
And just checking here, there's no actual gecko toes in this material, right?
That's right. Yeah, no geckos were harmed in this research.
Okay.
Yeah, so these are all materials that break down into components that our bodies are used to dealing with. So polysaccharides like sugars, lactic acid, and glycolic acid, these are products that our bodies naturally can metabolize and deal with. So they break down into those components, not gecko toes.
Okay. No, you worked in conjunction with CU Anschutz Medical Campus to test the treatment in mice. What were the key results of these early trials?
Right. So these trials were preclinical, which means that no human patients were used. So this first study was really focused on the safety and tolerability of this technology. So we wanted to just make sure that this material system was safe, that it wasn't going to clog the urinary tract, for example, that it would stick over the tumor tissue that we were interested in sticking to, and that the mice can tolerate this well. Our results demonstrated that they are well tolerated, and I think that portends well for their use in future studies. We did not do any sort of efficacy study this time, meaning that we didn't compare the performance of this to a clinical standard. And I think that would be the next step, given our results now.
Well, this material was developed with bladder cancer in mind, but what other medical issues could it be used for potentially?
I think any situation where you're in an environment where there is some sort of fluid exchange, where there is movement, for example, like in the stomach or in the GI tract, there could be some opportunity to deploy the system so it stays in the region of interest, even if fluid passes over it. So we're thinking the bladder was a good place to start for all the reasons that we talked about. But looking forward, we think that something like stomach cancer, something in the GI tract, and potentially other regions of the body as well would be a promising target.
Lastly, Wyatt, do you think pharmaceutical companies or researchers should look a little more closely at reptiles when they are developing new drugs or treatments?
Absolutely. And not just reptiles. I think nature is, it's one of those things. We live in Colorado, and I think we're fortunate to have so many beautiful things around us. And if anything, I hope this research is a reminder to step outside and look and see what there is to offer around us. And hopefully that can be inspiring to scientists, clinicians, and many other people in many other fields. I think there's a lot to learn just from nature.
Wyatt Shields is assistant professor of chemical and biological engineering at CU Boulder and part of the team that developed a new material that can cling to tumors to create more effective chemotherapy treatments. The technology is described in the journal Advanced Materials, although Wyatt stresses they've only tested on mice, not humans so far. We'll have more information in our show notes and at KUNC.org. We'll also include a link to a recent interview with a CU researcher who studies how python digestion could help us understand and treat heart disease in humans. That's it today for In The NoCo. I'm Erin O'Toole. Thanks so much for listening.